it's for a given input, you get a certain output. You want to give a proof that this computation will definitely give this output. So you have a prover. They want to prove that a program F, when run with an input X, will give an output Y. And the verifier knows the program and the I/O values, that is the input-output values X and Y. And in some scenarios, the verifier cannot run the program themselves. So you might ask that, why do I need a proof? So if the verifier knows the program and knows the input and the output, why can't the verifier just run the program on X and check that the output is Y? So due to resource constraints, it's possible that the verifier cannot run this program themselves. Or sometimes the execution of the program may require some secret information which the verifier does not have. So there may be insufficient information which the verifier does not have, or the verifier does not have enough resources. An example is a cloud provider, and the verifier is a user. So consider the case when the cloud is, so the user has uploaded maybe several terabytes of data onto the cloud, and the verifier just has a laptop. They cannot store all the data on their laptop, so they are uploading it into the cloud. But now they want to do some computation on that data. Maybe the data is all numbers, and verifier wants just the average of those numbers. Because the verifier cannot fit all the data on their laptop, they cannot run the computation themselves. So they ask the cloud provider, can you calculate the average of these numbers and send it to me? Now the output is just a mean, it's just a single number. Now the cloud provider may be lazy and say that, okay, I have 10 terabytes of data, all these numbers look the same. Let me just compute on 5 terabytes and send the answer. The verifier will not know that I did an incomplete computation. So the verifier in this case wants some kind of certificate or proof that the computation was run on all of the data. So the prover in this case will give a proof along with the output to prove to the verifier that they actually computed the function which was requested. And this is an example of verifiable computation. And the proof should be easier to verify than rerunning the function F. So this scenario works only if the proof is verifiable by the verifier on who is resource constrained, and it should be cheaper computationally to verify the proof rather than rerunning the function F. So the subfield of applied cryptography, which is used to enable this verifiable computation, is called SNARKs, or a technique you can say. SNARK stands for Succinct Non-Interactive Arguments of Knowledge. So succinct means that, first of all, there are protocols that enable verifiable computation. Succinct means that the proofs are smaller than the size of the statement. So the size of the statement in the previous example could be that compute the average of 10 terabytes of data. Now the proof should be much smaller than that. Typically, if you have the size of the statement is n, anything which is smaller in the sense if it is square root of n, that is considered smaller. Even log n is considered smaller. Log n is definitely smaller.
So your statement is the run of the program or program?
Yeah, it is the you can say an instance of the execution of a program. So it's because the code itself will be very small. Calculate the average, which is a for loop. But here you need to have you have to lay out the whole execution of the program. So and also they are non-interactive in the sense that there is a single message is sent from the prover to the verifier. The reason they specify this explicitly is that early cryptography protocols which enable these kinds of verifiable computation, they involve several rounds of interaction between the prover and the verifier. But in many applications, you just want the prover to just send the proof to the verifier. You don't require the verifier to be online and respond to the prover. Just as soon as the verifier receives, maybe he gets an email and we can just check it asynchronously. So it's non-interactive in the sense that it's asynchronous, just one single message, and the verifier can verify the proof at his leisure. And the argument refers to security or soundness. Soundness means that a malicious prover cannot generate a proof for an incorrect statement. So it is only guaranteed against probabilistic polynomial time. So PPT stands for probabilistic polynomial time adversary. So the prover is constrained to be a polynomial time adversary. So if the prover can do exponential computations, then they can generate malicious, they can generate proofs for incorrect statements. So there is another class of protocols where the prover can be computationally unbounded, but those are inefficient. So arguments are cases when the snarks are only consider the case when the provers are computationally bounded. That is a polynomial time algorithm. And the knowledge part refers to the prover knows a witness in the sense that to generate this proof, the prover actually knows the secret information which is required for this. So without knowing the information, they should not be able to generate the proof. Then it will be, that is, if this condition doesn't hold, then the prover could generate, if the computation involves some secret information like a private key, the prover could generate the proof without knowing the private key. And there is an attribute which you can associate with these snark protocols, which is zero knowledge. That is, ZK snark refers to a prover who can prove this without meaning anything except the correctness of the statement. So snarks in general are not zero knowledge in the sense that they may leak information about the secret information. But if you look at the subclass of snark which are zero knowledge, they don't leak anything except the validity of the statement. So the verifier, when they verify the proof, the only thing they get is that the statement is correct. That is, for a given input X, that output is Y. They don't know any other information about the program execution. So suppose I want to use this primitive, which is a snark. So the thing I need to do is that I have to express my statement or my program execution as something called an arithmetic circuit. What's an arithmetic circuit? So the circuit variables are prime field elements. I'll define a prime field in a moment. And the only operations which are allowed are addition and multiplication in this field. So what are prime fields? So just take a prime. Usually, typically this prime is very large. So 256 bit. The number of bits in the prime is 256. So it's just the integers from 0 to p minus 1. And the arithmetic is modulo p. By that I mean both the addition and the multiplication are so if you have xy in the prime field, then the multiplication is multiply the integers and take the remainder modulo p, and x plus y is just add them as integers. The integer may be larger than p, then take the remainder modulo. So the reason we are interested in this is that in these fields, because p is a prime, you can also find multiplicative inverses for all non-zero elements. So for any x which is in the field, but it is not the zero element, there exists a y such that x times y is 1 modulo p. So every non-zero element in this prime field will have multiplicative inverse. So x times y, x and y are integers in this range 1 to p, we are excluding the 0. X is outside this range, then y can't be 0 because if y is 0 then x and y will be 0 1 p. So x times y can be an integer which is larger than p, but it is guaranteed that when you take the remainder with respect to p, then you will get 1. You can check this easily by using properties of GCD. So arithmetic circuits are defined over prime fields, and the only operations they are allowed are multiplication and addition in this field. So we want to express to prove a statement using this snark. You have to express it as an arithmetic circuit. So let's see, because it seems like a very constrained model, but it turns out that you can express almost everything using arithmetic circuits. And R1CS, I'm going to expand on that abbreviation. It's one method for arithmetizing statements. So all snarks in practice, they first take any program or any statement you want to prove, and the first step they do is arithmetization. They convert it into a form involving prime field elements. Sometimes polynomials are also involved, and then they will apply some cryptography to prove those statements. Any questions so far? So what does R1CS stands for? R1CS stands for Rank 1 Constraint Systems. So the statement which you want to prove, I'll show examples as we go along. It will be expressed using many such quadratic constraints. So what is a quadratic constraint? It is a linear combination of some linear combination. I'll explain what those AIs and BIs are. And another linear combination is equal to, this is a product here. The product of two linear combinations is equal to a third linear combination. So it's quadratic in the z variables. So the AI, BI, CI values are constants. So the A, B, C values here, they are constants. So they are determined by the statement. Suppose my statement is I want to check that the average of some numbers is some value. Then the AI, BI values will have certain values. If I change that average to variance, then the AIs will change, but the ZIs may remain the same.
N is fixed.
Sorry? Yeah, N is, so if your program instance has N variables, so I'll just come to that. So N is the number of variables in the, N is number of variables which appear in your program execution. So once you fix your program execution, whatever statement you want to prove, then N is fixed, and you will need many such quadratic constraints. But typically, a single constraint, only few of these AI, BI values will be non-zero. Because you will be, each constraint will be saying something about at least few of the ZI values. So typically these linear combinations will be sparse in general. In practice, they tend to be sparse. So why is this? So this is a quadratic part, makes sense. So why is it called rank 1? So it turns out that if you write that equation as the linear combination as this A, if I put it into a vector and I write it as the inner product of the vector A and the vector 1 comma z. So zi's go from 1 to n, but this A0 is multiplied by 1. I'm explicitly pulling out that 1 because most of the that is R1CS, it requires something to generate constants, so that guaranteeing that there is a 1 in this vector means that you can always generate constant variable. So this linear combination can be written as inner product of this A vector and 1 comma z. This linear combination is inner product of B vector and 1 comma z. And if you rewrite this as this product of this row vector, column vector, this row vector and column vector. So the matrix you get here, that has rank 1. So that's why they're called rank 1 constraint system. So this matrix here, M, this has rank 1. It's a multiple of a column and a row. So how do we express how do we express statements? So let's look at a complicated statement for the context of this tutorial. I'm going to describe a hash function. It's a cryptographic hash function called SHA-256, and then as we go along, I'll describe how any statement involving that hash function can be described using a collection of such R1CS constraints. So SHA-256, it's a cryptographic hash function. So what are cryptographic hash functions? They're a way to map a long input string of bits into a shorter output called a digest, and the requirement is that you have to avoid collisions. That is, you have two distinct inputs. It should be infeasible to find collisions. That is, the smaller output should not be, it should be difficult to find two distinct inputs which map to the same small output. Collisions will always exist. If I have a input space which is larger than the output space, then just because of the mapping, the pigeonhole principle, there will be two inputs which will map to the same output. But what we want is it should be infeasible. It's not impossible, but infeasible in the sense that given the current compute power, it should not be possible to find collisions. Now, what is a collision is defined as simply as this, that let's say h is a hash function for some input which is input x which is not equal to x prime, the hash of x and x prime should not be equal. So how do cryptographic hash functions manage this? Because if you have a domain which is larger than the codomain, then it means that there will always be collisions. But the infeasibility is achieved by defining a large codomain. What that means is that suppose I have a 256-bit output length. So the length of the output is 256. Then the number of possible outputs is 2 raised to 256. So I just shown a description here. We have bin 0. This corresponds to all zeros output. And then I have bin 2 raised to 256 minus 1, which is the all ones output. So when inputs are passed to the hash function, you can think of them being dropped into these bins in a deterministic manner. But the number of bins is very large, it's 2 raised to 256. So what the hash function needs to do is that as long as the two inputs are different, even if they differ in a single input bit, they should be, the bits in the input should be processed in such a manner that they are super randomly dispersed in this large number of bins, such that if you take any two distinct inputs, it's very unlikely that they land in the same bin. And I'll go over some gory details of SHA-256 because I want to show the power of R1CS in some sense, in the sense that I have a complicated hash function. It involves a lot of logical gates and loops. How does that translate into an R1CS? Because R1CS seems to be a very constrained representation. You just have a linear combination times a linear combination equal to a linear combination. When I show you the details of SHA-256, it may not be apparent how one can map this SHA-256 algorithm into just a set of constraints.
The solution of this constraint is
the solution of the constraint is called a witness, but the proof will be smaller because the solution may be larger, is as large as the statement. You want the proof to be smaller. No, I have not come to that. So so there are proof systems which will, given your R1CS instance, you can just think of them as a black box that generate a proof which is constant size or it is logarithmic in the size, depending on some trade-offs. So SHA-256, SHA stands for Secure Hash Algorithm. It is a standard published by the NIST in the US, National Institute of Standards and Technology. It has 256-bit output, that's why it's 256. And it accepts inputs of length 2 raised to 64 minus 1. So the length of the input can fit in a 64-bit integer, that's what it means. And these are bit strings. It was announced in 2001. So it has two stages. There is a pre-processing stage and a hash computation stage. In the pre-processing stage, you will do a padding. You will take the message. It is a string of bits. This m is some string of bits. Its length is less than or equal to 2 raised to 64 minus 1. First, you will pad the input such that the padded input has a length which is a multiple of 512 bits. Because we are going to process the padded input in blocks of 512 bits. And then there is some state variable. So these are an hexadecimal. So each of this is 8 hexadecimal digits, so it's 32 bits. So there are 8 of those 32-bit integers. So 256-bit. This is state, some state. This is derived from the square roots of the first 8 prime numbers. So the reason for using the square root is it's an instance of nothing up my sleeve design. So the cryptographers usually view the US government with a lot of suspicion. So if the US government publishes an algorithm, they may feel that maybe there is a backdoor somewhere and the constants which are chosen such that collisions can be found. So by basing the initial state on some naturally occurring numbers like the primes, they are just giving the algorithm reviewer that you have not put in any backdoor. It's still possible, but just a way of convincing the verifier or the reviewer of the algorithm. So the hash computation, there is something called a compression function, which is defined for SHA-256. It maps a pair of inputs. The first input is a 512-bit message block, and the second input is the correct hash value, and you get the next hash value. So if the padded input is divided into n 512-bit blocks, so each of these n superscript I is a 512-bit block, then the hash computation is a repeated computation like this. So x0 is that value which is derived from the first 8 primes. I showed you the previous slide. Take the first message block, then pass it through this compression function. This compression function, it takes a final 12-bit input and the previous hash, computes the next hash. Then the first message block is consumed. Then take the second message block in the next iteration, and h1 you get h2, and you keep going until you exhaust all the message blocks. And this last hn is the output of the SHA-256 hash. So the hn is the final 256 bits is the output of the SHA-256 hash. Now the only thing which is remaining for me to specify is this compression function. So somehow this compression function should ensure that for any two inputs, these carded input blocks which are distinct, the final hash should be collision resistant. It should be very difficult to find two inputs which result in the same final output. So let's look at some building blocks. It's fine to not, you don't need to remember all the details, but I just want to show you the complexity of SHA-256. So there are U, V, W are 32-bit words. So SHA-256 acts on 32-bit words. So you need bitwise AND, bitwise OR, and bitwise XOR. You also need integer sum modulo 2 raised to 32. So when U plus V, if U and V are 32-bit, then there can be a carry, but modulo 2 raised to 32 means that the carry is discarded. And treat them as unsigned integers when you do this addition. Then there is bitwise complement, and also there is a shift right and rotate right. So given a 32-bit integer, shifting right will insert n zeros in the most significant bits, and rotate right will just rotate the bits. So it's a non-lossy. This is a lossy operation. You lose some of the information in the U, but here you just rotate the bits n times. Rotate right the bits n times. Some more building blocks. So there is a choice function and a majority function. What the choice function does is that if depending on the ith bit of U, you will choose between V and W. So if the ith bit of U is 1, you will choose this AND. So you choose the ith bit of V, sorry. And if the ith bit of U is 0, then this becomes 0. This is XOR. This is ON. So you get the ith bit of W. So the bits of V and W are chosen using the bits of U as a switch between the two. So it's choice. The majority is, we calculate the majority of the ith bits. So you can check that this logical gate actually chooses if the ith bit in UVW, the respective ith bits are all 1, then the majority function will be 1. If two of them are 1, the majority will still be 1. If only one of them is 1, then the majority is 0, so you get 0. So it's a majority gate between three 32-bit integers. And again, some more complicated helper functions. So it's just you're rotate by 2, rotate U by 2, XOR rotate by 13, 22. So these constants is 2, 13, 22, 6, 11, 25. These are, it's difficult to justify the exact values in the sense that why not 23 here instead of 22. But this was specified by the SHA-256 designers. And in cryptography, it happens sometimes that you have to choose some constants. Sometimes the constants are motivated by avoiding certain types of attacks, but sometimes they're just arbitrary. There's no specific reason why that number is 22 and not 23.
What is SHR?
Shift right. The rotate right and shift right. So this is lossy district. Okay. So here is the details. So first, the function, the compression function. So I said that SHA-256 is, you have this iterated kind of structure. In each F invocation, one 512-bit block of the message is consumed. So what is that F? So first you will maintain an internal state of 64 words. Each word is 32 bits. And there are some other constants also we need, which are derived from the cube roots of the first 64 primes. And the compression function, each step, it will take a 512-bit block and the current hash or the previous hash and give you the next hash. So you initialize the WJ state like this. So the first 16 blocks, you just copy the message. The message has 16 32-bit blocks because it's 512 bits. just copy the first, those message blocks into the first 16 words, and then you apply those helper functions on the previous wj's. So wj for j greater than or equal to 16, j minus 2 will be defined, j minus 7 will be defined, and j minus 15 also is defined. So is j minus 16. So you can compute the remaining wj's using the previous values from j going from 16 to 63. This is the internal state initialization. And then you initialize some 8 32-bit words to the previous hash, that is whatever is there here, the previous hash. And then you run a loop 64 times. The details again are not important. I will show an R1CS circuit. I'll show the code where how this loop is actually implemented using Rust code. So there is, the thing to note is that there is a 64 loop which runs for 64 iterations, and this ABCD EFGH is updated in each iteration of the loop. It is updated using these values P1 and P2, which are computed using the current values of A to H, and we keep updating it. And you arrive after the 64 iterations, you arrive at a value of ABCDH. Just add those values using integer addition, modulo 2 raised to 2 addition, to the previous hash value to get the next hash value. So, and that's it. This is the SHA-256 compression function. So, this compression function, if you have a long message block, this will be applied again and again until you finally get a 50. And again, if you see that the complexity of this, it is just to ensure that even if your bits, message bits differ in a single bit, they differ within a single location, because of all this mixing of the bits which is happening, the final 256-bit output will be very different. And there is a demo you can look at SHA-256algorithm.com if you're interested about how these iterations happen. I'll not open that. So here is a sample output. So I just have hashed the string December dec 0 to dec 9. If you convert them into bits, all these characters 0 to 9, so 0 differs from 1 only in a single bit. And here I put the output of the SHA-256 using hexadecimal digits. So each digit captures 4 bits. So there are 64 hexadecimal digits here for 256 bits. So notice that even though these two inputs differ only in a single bit, the hash looks very different. And that is what we want. We want collision resistance in the output of SHA-256. So the SHA-256 is complicated, but it can be computed easily in the forward direction. Those operations were chosen. Remember that this was designed or announced in 2001. So the operations are chosen so that they can be implemented very easily in 32-bit processors. That's why it uses 32-bit words. So both in software and hardware. But it's difficult to invert. If I tell you a hash value and I don't tell you the input, because of all this complicated operations which are happening in this loop which is happening, you can't simply write equations for the connecting the input to the output and solve for them. It's very difficult to invert the SHA-256. It's also difficult to find collisions. At least so far nobody has found collisions. So the predecessor of SHA-256 was an algorithm called SHA-1. So some researchers in Google a few years ago, they found collisions in SHA-1. So SHA-1 is no longer recommended as a hash function for any real-world application. So any questions so far before I go to the R1CS for SHA-256? So again, you don't need to remember all the gory details. It's I just want to show you an instance of a very real-world and complicated circuit or algorithm which will be converted into a verifiable computation form using R1CS. So suppose I want to create a rank 1 constraint system for SHA-256. Maybe the application is proving knowledge of pre-image. That is, suppose you want to prove that I give you a hash and I want to prove that I know an input which will lead to this SHA-256 hash. For example, suppose I claim that, or maybe the captain of the Indian team, he claims that who will score the highest runs in the upcoming World Cup. Now, if he reveals the name of the highest run scorer, then maybe it will undermine the confidence of the other players. So he doesn't want to undermine the confidence of the other players. So what he'll do is that he will So suppose I am Rohit Sharma and I want to say that maybe Rinku Singh will score the highest number of runs in the World Cup. So what I can do is that I will compute a SHA-256 hash of some salt value, this is some bit string, and the string Rinku Singh. The reason I'm doing that is if I directly announce Rinku Singh, the other players may feel that they've been slighted, and Rinku Singh also will be under pressure because the World Cup has not happened. So Rohit Sharma is making a statement about the future. So he doesn't want to affect the country. Say it again. This is concatenation, string concatenation. So I'm just concatenating a salt value. This will be some large bit string. Large in sense, let's say 256 bit string. So that this salt value should be long enough. It's a randomly chosen bit string, 256 bit string, so that it's large enough so that people cannot brute force the value of the salt. So I'm going to reveal the hash. Maybe I'll post it on Twitter. And later, after the matches, after the World Cup is over, I can reveal the salt and the name, so people can check that the SHA-256 hash of the salt value and the player's name is actually equal to that publicly revealed hash. So this is called commit and reveal. So you're committing to a value which is the name of the player, but you want to hide the commitment, so you're adding a salt which is not revealed, and later you will reveal it in the future. And because of the collision resistance of SHA-256, it's extremely infeasible. It's infeasible for Rohit Sharma to change the name of the player. Suppose Rinku Singh didn't score runs, maybe Shreyas Iyer scored the most number of runs. Now this hash, suppose this hash was revealed on Twitter. Now Shreyas Iyer is the player who actually scored the highest number of runs. Now if Rohit Sharma wants to pretend that he had actually chosen Shreyas Iyer, he has to find another salt some salt 2 such that these two are equal. So if he had initially created this hash using Rinku's name, and then later Shreyas turned out to be the highest run scorer, to save face, Rohit Sharma would have to find another salt value such that when he hashes SHA-256 with that salt value concatenated with Shreyas Iyer's name, you get the same hash. But because of the collision resistance of SHA-256, it's very infeasible to do. So proving knowledge is can have real world applications, proving knowledge of the pre-image. So you have a public void, the hash value which you have revealed, and you have to later claim that you know some x will be the sort concatenated with Rinku's name, such that this y is equal to SHA-256 of that. So how can I represent this statement in R1CS? So first let's start with the simplest gates. So if you remember, our SHA-256 had a lot of Boolean gates. So AND gates, OR gates. Actually OR was not there, but let's look at OR gates also. So first thing is that as in arithmetic circuits, all the variables are finite field elements, prime field elements, and only multiplication and additions are allowed. Subtractions are also allowed, because subtraction is multiply z with -1 and add that. Now if I have a constraint like this, where if I say that z is a prime field element which satisfies this constraint, z into 1 minus z equals 0, that means z is forced to be a bit. It is going to be a 0 or a 1. It's only two possibilities for z. So suppose I have two bits given by two constraints. So notice that this is an R1CS constraint, because z is a linear combination of the variables. 1 minus z is also, remember we allowed the constant 1, because a0 can be set to 1, and 1 minus z is also a linear combination, and 0 is a trivial linear combination. So product of two linear combinations is equal to a linear combination. So this is an R1CS constraint. I have two R1CS constraints to constrain the value of z1 and z2 to be bits. And finally, the AND is just a third R1CS constraint. I say that z3 is going to be z1 into z2. So this z1 and z2, these are also linear combinations, and we get right hand side is a linear combination. So this is, in this way we can express an AND gate in R1CS. Similarly, OR gate is, you can check that once you have these two constraints, Z1, Z2 are bits, a constraint of this form will ensure that Z3 is the OR of Z1 and Z2. You can check that. So when if Z1 is 1, I get 0 on the left hand side. Then to get 0 on the right hand side, Z3 also has to be 1. Similarly, Z2 is 1, irrespective of the value of Z1, left hand side is 0, so the right hand side Z3 has to be 1 to make it 0. If both Z1 and Z2 are 0, left hand side is 1, 1 minus 0 into 1 minus 0, and then right hand Z3 also has to be 0 to make the right hand side 1. So again, the OR gate can be expressed using this R1CS constraint. So any questions about this? About XOR and NOT gates. XOR is slightly it's a little clever. So you can, this is the constraint for XOR. So Z1 plus Z1, you can write it as 2 times Z1 is this 2 times Z1 times Z2 is Z1 plus Z2 minus Z3. Again in RLCS form, you can check that suppose Z2 is 0, then Z3 should be equal to Z1. That you can check easily. So suppose Z2 is 0, then this left hand side becomes 0. So Z2 is 0, then Z1 minus Z3 should be 0. So Z3 is equal to, supposed to be Z1. Similarly, if Z2 is 1, so on the left hand side we have 2 times Z1. So if we cancel one of the, here we have Z1 plus 1 is 2 times Z1. So you get Z3 is 1 minus Z1. So this is OR, XOR, and NOT is easy because it's just say that Z2 is 1 minus Z1. So that is just the NOT of Z2 is the NOT of Z1. So in this way you can construct all the gates which are required for Sharp physics. But Sharp physics also had 32-bit addition. There is modulo 2 raised to 32. That is, you add two integers and throw away the carry. So how can I do this seemingly complicated operation of checking if the carry bit is there and throwing that away? So the solution is easy in retrospect. So you write a 32-bit word not as a single field element but as a vector of 32 booleans. You have 32 constraints to describe the 32-bit word. So you have U0 to U31. Each of them is a bit. So there are 32 constraints to constrain them to be a bit. So each of these U0, U1 will have a constraint of the form U0 into 1 minus U0 is 0 and so on. So you constrain all of them to be bits using 32 constraints. Then suppose I want to do operations involving 32-bit words, then you just do bitwise, that is component-wise operation. I already showed you XOR and NOT. So use that on the component itself.
Once you have implemented NOT and OR, you are done.
Yeah, but if you just brute force use NOT and OR, then the number of constraints will increase, and typically the proving time depends on the number of constraints. The metric you want to minimize is the number of R1CS constraints used to describe your statement. So you're right that NOT and OR, then it is complete in the sense that any statement can be described. But if you do, suppose like 32-bit addition, if I implement it the way circuits are implemented in practice, then the number of constraints will be much more than the algorithm I will show. You want to take advantage of the fact that you have a prime field. So in a prime field, you can do additions for free in some sense. Even rotate right is, you have these 32 booleans, so just move them around. You just define another 32-bit vector which has the equality constraint according to the rotation. And let's look at addition. So addition, here I'll show how to take advantage of the field. The fact that U and V are they are 32-bit. There are 32 booleans represented using 32 boolean variables. But you have at your disposal a field which is typically much larger than 2 raised to 32, and you can use that to reduce the number of constraints. So suppose I wanted to calculate W, which is U plus V mod 2 raised to 32. Assume the field is much larger than 2 raised to 32. Typically typically it's 256-bit field. So first you calculate a field element using a linear combination. So this is again an R1CS constraint. So I suppose I define small u as a linear combination of powers of 2 and this ui bits. So each of these ui's, they are field elements, but they are constrained to be bits, so they're 0 or 1. So I'm generating an integer kind of field element which is equal to this the integer representation of u. Similarly, get the field element corresponding to v as a linear combination. Each of these costs one R1CS constraint, and then now allocate 33 bits. So the sum of two 32-bit integers will be can occupy 33 bits. So I'm going to allocate 33 bits. Each of them will cost one R1CS constraint. The index was from 0 to 32, not 31. So there are 33 of them. Then finally, then get the W value also. Calculate the field element corresponding to this. Then check that W is equal to U plus V. That is, this is another R1CS constraint. So W is a field element, V is a field element, U is a field element. So this can be written as U plus V into 1 is equal to W. This is also one R1CS constraint. Then finally, what we want is the mod 2 raised to 32. So that is, you just throw away the 33rd bit. So just give the output as W0 to W31. So each 32-bit integer is going to be represented using 32 Boolean variables. So here W has 33 Boolean bits, but I want only the least significant 32 bits. So just throw away this W32. Just go from W0 to W31, and that is going to be your sum. Now, if you count the number of R1CS constraints, this is 1, 2, 3, and 4. Truncation is the keeping of the variables. There is no constraint. Just going to take that 31 variables and move them around. So 1, 2, 3, 1, 2, 3, and 4. So using 4 R1CS constraints, we can do a mod 2 raised to 32 addition. But if you were to do it using AND and NOT gates, it's going to be much more. In the sense that you calculate the carry bit and check if the carry bit is. Again, you can discard the carry bit, but you have to do the carry. That is, if I were to add them as bits, then if both U and V have ones, then I have to move the carry around. So all that complexity is of the carry is being captured in this U plus V in the field itself. So that is approach which we took for SHA-56. Any other questions in this?
What's the carry now?
So the carry is, so we are doing this, this prime field is, so U plus V. If the P is much larger than 2 raised to 22, then that will manage the carry. So it is just integer addition. So suppose I want to add, then here, so I add, this is the VCB 1 and then 1, and here the carry is happening, right? 1 plus 1 is 1, and here I'm getting this 1 plus 1 is 0 and 1. So this kind of carry. But this, when I do the U and V conversion, suppose this is U and V, I'm writing only 4 bits, and this is 1 plus 4 is 5, and this is 2, 4, and 8, right? So this is 13. So I'll just add directly in the field, in the prime field FP. So x plus y is x plus y mod p. So if as long as p is much larger than 2 raised to 22, the mod p will not matter. When I do x plus y, the taking remainder x plus y, this will be equal to, the remainder will be equal to x plus y. So 5 plus 13 will just come out as, I made some error I guess. So this 14. It's a 14, yes, it's an even number, right? Yeah, even number. So it's 19. So how is the carry managed? So basically the addition is happening in the prime field here. So that automatically that we don't think about the bits, the carry is being handled implicitly in the addition itself. So we don't have to explicitly worry about the carry going to the next step. So suppose now you want to prove these R1CS instances. So suppose you can generate a collection of R1CS instances. You have to collect all of them. So like even in the simple AND case, there were 3 R1CS constraints. 2 constraints to force the bits, the inputs to be bits, and the third one to be the AND. So you have several R1CS constraints of them, tens of thousands. What the only change I've made is I've introduced another index J here. So previously I just said linear combination is a linear combination is that. So there was only a single index, A0 and AI was there. But now I have n constraints. I've changed this variable to n. So this is the jth R1CS constraint. So AJ0 and this is AJI. J remains the same in this constraint. This is the jth R1CS constraint. So typically in a statement you want to prove there will be several of these R1CS constraints. So you have to collect all of them. And you suppose I make a matrix out of these matrix A out of these constraints. So what I'm saying is that these AI which are appearing in the J linear combination, make a matrix where this is A1, the first row is when J equals 1, and the second row is when J equals 2. And so on. So there are n such rows. I'm assuming n constraints. So you construct this is going to be the matrix A. Similarly, use the linear combinations, the constants in the linear combination in Bj's and Cj's to construct these matrices B and C. So in R1CS instance, there is a collection of all these constraints. Is going to be the Hadamard product of matrix A with the Z vector, which is actually Z is 1 comma Z. So I think Z should be Z vector is there is a constant also. I forgot to add that. So you can once you have these matrices A, B, and C, I'm saying that take the A matrix multiply by the same. So multiply the matrix A by the Z column vector. So then the components of that resulting column vector, the first element in that will be this first linear combination for J equals 1. This will be the first element of this product. AZ will be the first linear combination of J equals 1. Second element in that column vector will be the second linear combination. Then you are taking Hadamard product, that is element-wise product of those two column vectors. So AZ will be a column vector, BZ will be a column vector, and CZ is a column vector. So you are writing this as some matrix equation. So you have collected all those R1CS constraints, and you have this final equation. This can be proved using various proof systems. So one proof system is it uses something called elliptical pairings. And Jens Groth is a computer scientist, a Danish computer scientist who published a paper in 2016. It's a improvement of schemes which were first revealed in 2012 by some researchers in IBM and Microsoft. So Groth-16, the main improvement was that it reduces the size of the proof. It uses a specific cryptographic technique called elliptical pairings. And it can prove. So if you give me this AZ into BZ is equal to CZ, you give me an R1CS instance, you give me these matrices A, B, and C. Then if there is a witness Z or Z which satisfies those constraints, then you can prove that you know that witness using something called Groth-16. The advantage is that the proof size is just 3 group elements. So each group occupies about 32 bytes. So within like 200, actually I think 64 bytes. So within about 200 bytes is the proof size, irrespective of the size of the statement you want to prove.
Is not there.
Reading from memory, it is not there, but there is something called they have something called lookup tables, and they use a primitive called offline memory checking. Whenever they need memory, there is this old paper with double comment. So offline memory checking is that if you have a memory, then you can prove that that memory was accessed in a consistent manner. You have reads and writes to a memory, and so there have been systems which have used that. This GOT16 doesn't have that reading from memory, but if you notice that our Sharp physics had some loops and some variables were being updated. So it seems that memory is being accessed. So the way out of it is that you just unroll all the loops, write down, create a new variable for every change in the memory location, and then prove the. Yes, yeah, I can see that, yeah.
How do you know they match with actually what is stored in the
Yeah.
that part is missing?
Yeah, so in that case, in that example, the verifier would have to have some hash of the data, because otherwise, even if I prove that I added some terabytes of data, it could be any data which, yeah. So there, in that case, when the verifier is uploading the data to the cloud, every time they upload or before they upload, they compute the SHA-256 hash of the data and then they upload. Let's say when they're uploading those like photos, they were uploading or numbers, which is only then.
One more thing that is also missing here. I mean, I have maybe finished that I know.
Yeah.
Is it actually enrolling of the program?
Yeah, it is enrolling of the program.
How do you know it's actually enrolling?
In the sense that the verifier which has access to the circuit, ABC values.
They have access to
ABC. Only the Z's are the instants which are secret. The constants depend on the statement. Yeah, and they can. But there is a con. I mean, it seems like you're getting something for free. How can it be that you can get a constant proof size irrespective of the size of the statement? So there is a pre-processing step called a trusted setup, and this involves you need a committee of participants to generate some randomness, and then they have to somehow throw away that randomness. So the way it is generated, this trusted setup works is as long as one of the participants is honest, then the trusted setup is safe. So when Zcash was a pioneer in this, they deployed a real-world system using this trusted setup. They use a predecessor of GOT16, but same pairing-based, they use elliptical pairing. So they had 5 well-known community and academics and industry people who each participated in this trusted setup, and then they destroyed their laptop in a public manner and so on. So if all 5 were to collude, then the trusted setup is it can be subverted, as you can generate proofs for wrong statements. So that is the con of this. But later schemes came and they removed this trusted setup, but at a cost of increased proof size. Like Spartan is a snark from it was published by Srinath Sethi, who is a Microsoft researcher. He's in Microsoft research. So it doesn't have a trusted setup. That is one of the biggest gains. But the con is that the proof size is square root now. So if you have a statement of size n, then the size of the proof is no longer constant, it is square root of it. So as long as you can take this cost, then you can get rid of this trusted setup part of it. So RNCS, you convert your statement into RNCS, and then proving it involves using some smart systems. You have many choices. GOT16 is one choice, Spartan is another. GOT16, the advantage of GOT16 is that GOT16 proofs can be verified on Ethereum. Ethereum is a blockchain where we installed a elliptical pairing check, so that you can verify proofs in smart contracts. So that has opened up many privacy-based applications, like Tornado Cash is based on this. Spartan proofs are too big to be, currently they are not verified, they can't be verified on any blockchain currently. But people are working on a verifier, this Lurk Lab people are working on a verifier to be, for the Spartan proofs to be verifiable on Ethereum. So this bell paper, so today's talk was about the bell paper. I have not come to that library yet. So the main takeaway is that if you write your circuit or your gadget or the statement, circuit is just a synonym for statement. If you write your circuit using bell paper, then you can use any backend. You can use GOT16 or you can use Spartan. Both of them are available. So it is a general purpose front end for which supports multiple backends. Any questions about?
So I was expecting that to write a code.
Yeah.
You run the code and then it takes the run as an input.
Yeah. So it is like that. So you will write a circuit, and then there is a step called witness generation, which the backend will do automatically, and it will lay out all the circuit. And in your circuit, you can have loops and all that stuff. And the witness generation part of the ZI values will be generated, and you. Yes. So the AIs are part of the statement, and the ZIs are the witness values. And also another exciting thing about this R1CS is that it supports incrementable verifiable computation. What that means is, suppose you have a computation of this form. This looks like even Sharp physics has this form. This capital F was of the form, it was a compression function small f. So IDC is a 2008 paper, it was introduced in 2008 by Valiant. He said that suppose you have this this kind of structure for your computation, then he gave a way of proving this computation efficiently. So what is the structure? You have the same function f is repeating. You have some witness values. These are called it's a public input z0, and that is converted to z1 with a private witness w0. Then z1 is converted to z2, and zi is converted to zi plus 1, and finally zn. So given capital F, z0, zn, and the number of steps n, you want to give a proof that this zn is consistent with z0. So it's incrementally being computed, and the solution he gave was expensive computationally. But recently in 2021, I think, again Srinath Sethi, the person behind Spartan, he proposed something called a folding scheme. It's called NOVA, and this can be used to compress this computation of this form. So this computation has some repeated structure. And if I were to build an R1CS circuit for this structure, then the size of the circuit will be proportional to n. It will be proportional to the number of invocations of the function f. Suppose this function f involves 10,000 R1CS constraints, and if this n is, let's say, 5, then 50,000 R1CS constraints will be required to prove this computation. But this NOVA folding scheme, they said that you can, there is a way to fold all of this computation into a single relaxed R1CS constraint. So to support folding, you have to make a slight change to the R1CS. I'll not go into the details, but it is just the ABC matrices. You have another vector E, which is a relaxation vector. And then after folding, the size of this folded instance is, I do not have the slide there. So this the size of the folded instance will be independent of the number of steps. Suppose this capital F involves 10,000 R1CS constraints, the folded instance will also be proportional to 10,000, and the proving time will be proportional to 10,000. And if you use Spartan, the proof size also will be square root of 10,000. So this was a recent development, and it turns out that many applications have this repeated structure. So this is, and bell paper circuits, if you can express your circuit in bell paper, they can be proved using NOVA also, and this definitely increases the set of application areas where you can apply these snaps. So all the previous snaps like dot system, the amount of memory required to prove was in the order of gigabytes. So when as your circuits got larger, it got tougher to prove the statements. But using folding, you can reduce the resource requirements by just using this NOVA folding scheme. And I think I don't have a slide on that, but then there was a subsequent paper called Supernova where they relaxed this uniformity in the implementable in the IDC. The uniformity is that the same function f is being called in each of the steps. Supernova was, they said that you can call one out of some n functions, and you can still do the folding. The proof size increases, but the size of the circuit which is here, that is reduces. So that is called Supernova, again from the same team from Microsoft Research. And both Supernova and Nova, they support bell paper as a front end. So any questions about this part? The proof, actually I have not made slides for that. So that involves, for example, this in the Broad 16, you have to convert that into a polynomial form. You have to do some polynomial interpolation to get some these ABC matrices. You get some polynomials and use elliptical pairing to check that. I can share some slides about that because I had in that Aptos Winter School I had given a description of Broad 16. So that's a different. So let's look at bellpepper. So finally, I said some Rust library. So where is the Rust part? So this is, like I said, the repository is here. It has two crates. Crates are like logical partitions of the library. Bellpepper core and bellpepper. And as I said before, bellpepper is a descendant of bellperson. So the core functionality of bellperson was extracted into this bellpepper core, and now bellperson itself uses this core functionality. And the library is not, the bellpepper core library is not very large. It's just a few files. You have some benchmark libraries. This is for benches are for testing. Then you have the cargo toml file, and we have the source directory, and not a lot of code here. So you have some gadgets, a Boolean gadget, and then the number gadget. Then LC stands for linear combination, which because R1CS involves linear combination. And then you have some util, and there's something called CS stands for constraint system, which I described. There's a way to test this test constraint system is for you to test your R1CS that you do not make any logical error when you wrote this constraint system. So first let's look at variables. So the thing about verifiable computation is that there are two types of variables. Some are public and some are not public. Suppose I want to prove that xy satisfies this equation, x cube plus x plus 1. So an R1CS for the statement is, you can't do cubic in an R1CS because R1CS is only quadratic. So first I will generate an auxiliary variable x2, which is the square of x in square of x, so x times x. Then I will generate another auxiliary variable x3, which is x cube, so x2 times x. So both of these are different R1CS constraints. Then I will generate that x3 plus x plus 1, which is the right hand side here, times 1 is equal to y. So this y is another variable. So this is the way I would verify that this equation is satisfied. Now the x and y are the inputs because we are proving we are saying that we have this x and y values which satisfy this equation. They will be known as the inputs, and these x2 and x3 are auxiliary variables. They are not part of the statement which is being proved, but they are required to prove the statement. So they were generated in the process of proving the statement. So this is the kind of unrolling we are doing. In many proof systems, in both Broad 16 and in Spartan, not in the current implementation, but in the paper, the one they described in the paper, auxiliary variables can be kept private, but the inputs are public variables. So the statement needs the public I/O. Requires what is part of the statement is all the variables which are part of the statement have to be made public, but these auxiliary variables can be kept completely secret. And the thing about verifiable computation is that outputs are also inputs. What I mean by that is, suppose we want to prove that y is the hash of a salt value r and some input x, then it appears like y is the output of the computation. But the R1CS instance which you generate will take x and y as input variables and r as auxiliary variable. So in some sense, even though we have some function and some output is being created, in the verifiable computation, y will also be an input to the verifiable computation. And there are other auxiliary variables which are not in the statement. So because the Chartered-Physics computation involves a lot of gates and integer addition modulo 2 raised to 32. So a lot of auxiliary variables will be created as part of that. I think the number of variables in a single Chartered-Physics invocation is about I think 20,000, if I remember correctly. So how do I describe a variable? So this is in this file, bellpepper core source and linear combination.rs. So variable is just first we need an index. I said there are two types of variables, right? Inputs and auxiliary variables. So there is an enum which differentiates between these two types of. There is an index of an input and an index of an auxiliary variable. And U size is 64-bit in most architectures. So this enum has input and auxiliary, and it captures a integer in that enum. And a variable is just it's called a tuple struct. I didn't show this kind of struct yesterday. So it's a struct which has a single member. So in that case, you don't need that. You don't need a name for that. So this struct, it's called a tuple struct. It is a struct with name variable, and it has a single member which is a public member whose type is index. So if you want to access this type of struct, you just put .0 and you'll be able to access the member. So this is how variables are defined in bellperson. How about linear combination? Suppose I want to describe a linear combination in code. Again, same place. So the linear combination is just going to be. So ignore the second one, this last inserted. That is just some variable or some data which is used to optimize operations. But a linear combination is simply just a vector of indices and this a value which is going to be, this is a type, it's a generic type, a value of type t. Actually, this is the indexer, not the linear combination. So the indexer is just a vector of indices and some type. And last inserted you can ignore for now. But the linear combination itself is, there are two indexes. One is for the inputs and one is for the auxiliary variables. Again, they separate the two because one of them, in most proof systems, one of them has to be kept private. So they're keeping the two. The linear combination may involve linear combination of inputs and auxiliary variables, but they're just keeping them separate so that they can be used by proof systems to ensure privacy. So linear combination is two indexes, and each indexer has a list of, here I have inserted scalar in the indexer type. So if I insert scalar here, I am getting a vector of indices and scalar values. So you can imagine that this is just, if you, in the linear combination, if you have AIs here, the AIs are that scalar. So I said you have some summation AI is here and summation BI. So in the linear combination, I need to know which variable is being multiplied by what constant. So that is captured in this. If I insert this scalar here, the variable's index is in the U size, and I have different indexes for inputs and outputs. So the index of the variable in either in the input vector or in the auxiliary variable vector, that is captured by this U size, and the coefficient is captured, this AI is captured by this scalar. And the scalar, if you notice, if you remember yesterday's syntax, this is a generic variable, but there is a trait restriction, it has to be from a prime field. Scalar is a prime field. And the prime field is defined in something called the finite field trait, FF trait. So I'll not say more about that. So imagine that there is it's a trait which can be implemented by many implementations. So many structures can implement this. So as long as you have this type which satisfies this prime field constraints of the prime field trait, then you can initialize a linear combination using these variables, this structure. Any questions about this? Assume that you came for yesterday's talk also. So let's look at a test constraints. Yeah.
In the previous slide, how scalar related to the indexer?
So it is like, if you remember, this is a generic enum. So the indexer had the definition that T was in the indexer, right? So indexer is a collection of it's two field elements. One is a vector of tuples, And the first, this is the vector of this. So what this means is that it will be u size p, u size p, and so on. This is an index set. That is, the values in the index set is a vector of tuples like this. The first type is, in each tuple, the first element is u size, second element is some type p. So when instead of p, if I put scalar, what I mean is that this p will be replaced by scalar values. So if I put, for example, if I put index at f64, some floating point, then this will be a vector of u size and f64. But since you want linear combination, we want scalar because the AI values will be captured in this. When I put scalar here, the C will become a scalar. So here this u size will be the index I, which will extract this variable or auxiliary variable value, and then the AI will be the scalar we are multiplying. Then suppose you write some circuit and you want to test it. So bellpepper core allows you to test your circuits. You have to, this test constraint system, first I have to describe what is a constraint system trait. That is in this file. This slides I'll share so that you can look at these later. So this constraint system, it models a R1CS instance. So it has a function called alloc, which will allocate a auxiliary variable. It has a function called alloc input, which will allocate an input variable. And then there is an enforce, which will enforce an R1CS constraint between three linear combinations. So there are some other functions in this trait, but these are the main three which are required to for our context. The test constraint system is quite a busy structure. I'll just go over it step by step. So first there is the inputs. So you have again a vector of the input values are there are some prime field elements, so they are scalars, and there is a label associated with that. So labels are usually used for debugging. And then there is also a vector of another vector of tuples of scalar string tuples. These are the auxiliary variable values and some label associated with that. String label associated with that. Then there is constraints. So each constraint is of this form. It is a linear combination times a linear combination is a linear combination. So that is what it is. This is A, first linear combination, second linear is the A's, the B's, and the C's, and then there is again a label associated with that. And there are many such constraints. So it's a vector of such triples of linear combinations and string labels, or actually 4 tuples. A vector of 4 tuples. The first 3 are linear combinations, and the last one is a scalar. And there is a hash map of which maps strings to named object. I am not shown the named object. Again, this is for debugging. So what the test constraint system does is that it associates labels with every variable, every input, every auxiliary variable, and every linear combination. So all string labels are for debugging. So what happens is that suppose I write a complicated circuit using this test constraint system, and that AZ times BZ should be equal to CZ, and it fails somewhere. Somewhere the constraint is not satisfied. Now how do I debug that? So the test constraint system, using these labels, it will tell you which constraint failed. It will say that this variable with this input with this string was allocated twice, or it was or a linear combination with this particular label did not get satisfied. So using those labels, you can debug your code. I have an example which I can show. Like for example, let's take this. I'll also show it in VS Code. But let's look at this test constraint system. First I import the test constraint system from bellpepper core. So bellpepper core, and in the test CS trait, there is a test constraint system, and I also import the constraint system trait from that trait. Then I need a prime field. So I am taking a particular prime field which is defined in something called the pasta curves trait. We are not using any curves here, but just that FQ. FQ is going to be a prime field. Think of Q as the size of the field. So I'm importing some scalar from this crate as f2. So the rest of the code, this f2 represents a prime field. Then I initialize a test constraint system, the new one. Then I allocate 3 variables. A is a variable. So it's a complicated, so then it seems like it's very busy, so let's break it down. So test constraint system, it's a mutable variable is allocated. Then A is cs.alloc something something something. So the first argument is actually an anonymous function. This syntax, the double pipe, if you put a variable inside, that will be an input to an anonymous function. The double pipe is empty. So this anonymous function is taking it's going to return the string all the time, every time. And then this is the second input is also an anonymous function which returns a finite field element which is obtained by converting the unsigned 64-bit integer 10. From 10 you get a finite field element, convert 10 integer 10 into a finite field element, and then this allocation may fail. So that's why there is unwrap here. So you want to ensure that this succeeds. Then similarly you allocate B and C. So 10, 4 and 40. I have allocated 3 variables. So why are anonymous functions used? Again, it is a quirk of the library. I'm not sure about the design choice here, why they chose that. The bellperson code library uses this kind of a way to allocate variables. They could have taken directly values, but I don't have an insight into why they chose this kind of allocation. It is from the Bellman library, the initial library written by Zcash. The same pattern is being repeated. Now, I just have variables now, but notice that 10 times 4 is 40. So I'm allocating these variables and I'm checking that A times B is equal to C. So cs.enforce is, again it takes three anonymous functions as input, actually 4. The first one is a label to the anonymous function, to the linear combination. This is a label of the linear combination, and this is the actual body of the linear combination. So it will take the first 2 linear combinations, multiply them, and check that it is equal to the third linear combination. And then finally, it will check if the constraint system is satisfied, and it will also allow you to print the number of constraints. There is only one constraint we are enforcing, one R1CS constraint. So it just this should be equal to 1. So assert equal CS or num constraints is 1.
What do you mean by dissatisfied?
Satisfied is AZ into BZ equal to CZ. So that that matrix equation is satisfied. Yeah. So if I'll just run this using actually and change the constants, and you'll see that it will fail sometimes. So this is the same code I showed, just the formatting is a little different. So I can run this. I can compile and it will run. And it ran, so this one did not fail. So suppose I change these values here. So here it is 10 and 4, right? Let me make this 5. If I run this, it said that the main thread panicked, assert failed, it's satisfied, constraint system is not satisfied anymore. So I'll just change this back to 4. If I run this, it passes in the sense that it doesn't, I'm not printing anything when it passes. So this is what I'm doing is that when for the prover is, so this is a test constraint system. So there's no prover or verifier, we're just checking that the constraint system is consistent. This is A times B, Z times B is equal to C. So these values are consistent with those linear combinations. So this is one way to test your circuit, create a small circuit, then you can test that. I think it's maybe 10:30 is when the tea is available, so maybe we can break a little early and have an extended break because I don't have too many slides after the break. Then we can meet again at 10:45 to continue. So I'll just describe some more syntax about how to express surface. We can break now and we continue at 10:45. Okay, so let's continue. So far I showed you this test constraint. Oops. Yeah.
On the link, the slides are
Oh, really? Okay. Is the server not opening?
it is just blank screen.
Okay. I'll check that because I think that is a department server. In the morning that was not working. But here the slides should be visible in some time. I think. Oh. Okay. I'll leave on the side. I don't know what I can. Maybe I did not create it. Oh wait. Try now. That's okay. Sync. So I said we can have test constraint system. I showed you some allocation of variables, but you can also allocate a variable and have a value associated with it. That is called allocated num. It is in this repo here. So the difference between just a pure variable and allocated num is you can carry around a value associated with that. If you remember yesterday's this option even. Option is something which can have either a null value which is none, or it can have a value which is specified here, a value of this type. So it's either a scalar value or it's a none. That is an option. So this allocated num is a variable, but it also has an optional value associated with it. And it allows the tracking of a variable in a computation. So what does that mean? So let's look at the same example as before. 10 times 4 is 40. What I've done previously, I had cs.alloc, which was giving me a variable, but now I'm allocating using this allocated num. So as before, I have now this allocated num.alloc. It takes a constraint system as a first input. Let me open this in VS Code so you can see the type of alloc. So this allocated num alloc, it takes. It is taking this is the alloc function. It is taking a constraint CS, the constraint system. It takes a constraint system as a first input, and then a value as a second input, and it will return. The value is not a value. It's a value of type f. What is an f? F is actually an anonymous function. Is f1 function once is a function which is going to return either a scalar or a synthesis error. Result is it wraps OK or error. OK of type scalar or error of type synthesis error. So here it takes two things: constraint system and a anonymous function. So constraint system is I need to specify a constraint system, but if you try to allocate a variable in the same namespace, because we are going to use these labels for debugging. If you try to allocate a variable in the same namespace, then you get an error. I forgot to show you that. For example, here, let's go to the previous one. Here I allocated a var and b var. These are the strings which I set for, which I use for debugging. Suppose I change this b var to also a var. So what is now happening is I am allocating two variables at the same namespace, the same string which is used for debugging. This will fail with an error. So the error, if you can see here, is it says that try to create an object at existing path AVAR. So what has happened is that I already had a object at AVAR, and when I forgot to change this AVAR to some other string, it complained. The reason is that the test constraint system ensures that there are unique, using that hash map, every variable and every linear combination is allocated to a unique string, so that when later when you want to debug and say that this value failed, or this constraint, this linear combination failed, then these unique variables, unique string values can be used to do the debug. So here, coming back to this, so I need to give a constraint system as input to these allocate num as the first argument, but I gave different namespaces to the two constraint systems, and then I give the values, which are anonymous functions with particular values. Then the difference between this example and the previous one is, here I am multiplying the allocated num directly to the allocated num b. I don't have to calculate the value 40. So 10 times 4 is 40. The previous example I had to explicitly calculate that value and put it here in C, but here when you use allocated num will in the background do all the calculations on its own. So you don't have to keep track of all the actual values. You just keep computing using these allocated nums, and the values will be generated on the fly. So just another convenience. So you can run this and check that it works. So you allocate B, then allocate C. You don't have to worry about the value of C. When a.mul is a method in allocated num, it will automatically populate the value of C based on what the values of A and B are. And then you can get the value of C and check that it is actually equal to 40, and that the constraint system is satisfied. So this is allocated num, but sometimes there is also another number which is instead of a value. One thing in R1CS constraints is that there is no need to allocate a new variable for a sum of variables. What I mean by that is, suppose y is equal to x1 plus x2. It looks like this is a linear constraint, one R1CS constraint, but because finally this y will be used in a linear combination, wherever y appears, I can replace it with x1 plus x2. So there is no need to explicitly allocate a new variable for x1 plus x2. If you can just keep track of what sum of variables y is, you can just replace wherever y appears with x1 plus x2. So that is captured in this structure called num. Instead of so before I had variable in allocated num, I had variable and I had a value here. The value is the same, but instead of the variable, I now have a linear combination, and a linear combination actually is a linear combination of variables. So this way, when I add two nums, then just the linear combinations will get updated. We don't have to allocate a new variable for that, because that involves some cost and it increases the size of the circuit. So again, some convenience and some clever way of optimizing linear combinations, not allocating variables for every linear combination. So here is an example. So this is the adding of nums. So what happens when you add nums? So this is actually a method in num. You add, the first argument is self. So the way you would call is a dot add some b. So other is the second argument. It is going to return a num, a type of num. So first the linear combinations of self and other are added, and then the value of the sum has to be calculated. Now we recall that the value was it's an option, so it can be null sometimes. It can be none or it can be an actual value. So you match you match on the values of self and other. If both of them are sum, then you just add them. If either of them is none, then you that is one of them is a sum and the other is a none, you just return the value of the sum. If both of them are none, then you return the value of none. And this the output of this match is being assigned to value. So then you create a new num with that value and the linear combination which we calculated here. So this is a way to add variables or add nums. So when some variable or some number is already a sum of other variables, you can use this num to reduce the number of constraints. Any questions about this? Yeah. So again, I mean, it's a lot of information in a very short amount of time. So slides are shared. So do look at it. There's a lot of clever ideas which were used to arrive at these design principles. It may not be obvious the first time you see it, but that's pretty fun. So what about bits? So there's something called allocated bit. It models a bit, a value which can take a variable which can take value 0 or 1. So again, it is similar. We have a variable and its value is it can be none, but it will be a bit option bool, so it's either true or false. And it has some methods like AND, XOR, NOT, and not. You might wonder why is OR not there. And so the reason it is not there is that you can compute OR using these functions, but also this it's from historical reasons. So the Zcash team, they had a very specific requirement. They needed only SHA-256, and in SHA-256 they did not need this OR gate, so they did not implement it. So what is an allocated bit? If I wanted to allocate an allocated bit, what will happen is you will call alloc function. It has again namespace, a constraint system as a first input and a value of a boolean as a second input. You will allocate a variable using the usual variable. So this variable will have value 0 or 1 based on the value which is passed in. This value which is passed in is an option rule. Then because you want to allocate a bit, you want to force it to be 0 or 1. So then you add this linear constraint that 1 minus a into a is equal to 0. So CA stands for constraint system. Take the constant from the constraint system and then subtract the variable which is allocated in this previous line here, and then multiply it by variable. So 1 minus var into var is, this is the empty linear combination which is just 0. So that way you get an allocated bit. Then there is a boolean variable. So a bit is always allocated, but a boolean variable, it optimizes number of constraints. So there are three options. It's an enum which can have either an allocated bit, the not of an allocated bit, or it can have a constant value. So why this difference? Why not just use allocated bits? Again, for reducing the number of constraints. So when a bit is a known constant, that is irrespective of the value of the witness values, the z's, if the bit is always going to be a constant, like in SHA-256, the initial value of the hash was a known constant derived from the primes, then not allocating it saves one constraint. So if something is a Boolean value but it's a known constant, then don't allocate it, just use the constant rule. And if you have this negated view, then whenever a not operation happens, I will just switch between is and not, and that also saves one RLCS constraint. For example, suppose I wanted to look at the not operation in Boolean. It's as simple as this. So the not of a Boolean, if you were to do a match, if the Boolean is a constant, then you just convert it to a Boolean of constant is cut off here, negated value is the constant. If the Boolean is an is, then just convert it into the not version, and if it is already a not, then convert it into is version. So this way, this not gate actually does not involve even a single R1CS constraint. Because if you had to do it using R1CS constraints, then you would be doing something like, if I want to negate some variable a, then I would say that 1 times 1 minus a equals b. So then this will involve the R1CS constraint. But modeling this Boolean as just these three possibilities, there is no R1CS constraint being applied here. So that saves, I mean, we just want to reduce the number of RLCS constraints. Typically, the size of the circuit is the number of R1CS constraints. Then let's look at, so when you have the three options, how would you implement AND? So let's see how that works. So you have AND, it takes two inputs. So there's some syntax which I did not cover. You say it's called lifetimes. So this single apostrophe in A, that is called a lifetime because we have some references here, and A is a reference and B is a reference. This means that this reference has a lifetime which is specified with a lifetime variable, and this reference also has a lifetime variable. So this is something to do with ownership of data, which I briefly mentioned yesterday. So if you not worry about lifetimes now, so you match on the values of A and B. A and B are booleans. So if either of them is a constant, then AND of anything with a constant is a constant false. So you just return constant false. If either of them is true, then you return the other value because AND with the true value is always x. If one of them is a not, so if I'm doing AND with not B, so either it's A is value and B is not value, or A is a not value and B is his value, then you allocate, uses AND not, which is an allocated bit, and you apply it on that. If both of them are not, then you apply the NOR on A and B. If both of them are just a bit, then you just apply the AND from allocated bit. So using the, whenever you have a constant value, then you just use the shortcuts. That is, constant value with anything is a, that's something. So if it is false, it is false. If it is true, then you return the value. If they are allocated, then you use these tricks to calculate the AND of that. So any questions about this so far? Again, a lot of code, but just going over it so later you can look at it and try to understand all the tricks which are being used at a slower pace. So 32-bit integers, because SHA-256 is what we want to prove, so it is nothing but a vector of booleans, nothing surprising. It's a vector of booleans, and the value will be a unsigned 32-bit integer. Allocation is, so the allocation takes a 32-bit integer as a input, so you extract the bits. So you need 32 boolean values. So I'm going to take the match the value, and I run a loop 32 times, and I'm doing some bit shift operation, and I'm ANDing with 1. If that value is, if this is 1, you get a true here. If the least significant bit of val is 1, then I get a true here. I'm pushing that into this vector v, and then I keep val. I'm just right shifting it and reducing the value of this val which is matched here. So I'm just extracting the bits from the input value, and I'm matching on the input value. That input value was an option, so if it is none value, if it matches to none, then I just map it to a vector of 32 none values. Then once the values are the bits, then I use the iterator and I allocate 32 boolean values. So I get allocated bit, and I allocate a boolean from these allocated bits, and I return them. So this is the way to allocate a boolean 32. So finally, it's come to the SHA-256. So you have boolean gates, variables, and 32 bits. So how is the SHA-256 algorithm going to work? So recall there was 2 stages: pre-processing and hash computation. I said that first stage you have to pad the input such that it becomes a multiple of 512 bits. So the way it works is you are given a message of L bits length, you append a single 1 bit, then you append some 0 bits such that L plus 1, the length of the message plus that single bit you added, plus K plus 64 is a multiple of 512. This means that you appended K bits such that there is space for 64 bits. In that 64 bits, you put the length of the message. So you append the length of the message to the padding. So you know that the unpadding can be done. And then the relevant code is here. Let me see if I can. So this is in wallpaper, in the crates, wallpaper source, gadgets, and SHA-56. So this is the padding. So the way it works is input is a vector of booleans. Notice here, input is a vector of booleans, and then I convert that to a vector. It's a mutable, padded is a mutable vector, and then I calculate the length of that because I've append that. Then I push a single bit onto it. Then I append k zeros. I run a while loop until I append k zeros such that k plus L plus 1 plus 64 is divisible by 512. And zeros are basically boolean, which is derived from false. And then I convert the length as 64-bit integer and I push that bits corresponding to that into the padding message. So this is how the code would look like. So here you have an instance of a non-circuit implementation, and here is a circuit implementation. You just have boolean vector for the message. So you are padding a single bit, 1 bit, and some k0 bits and so on. I have to go back. In the hash computation, I said you have the padded input is split into n 512-bit blocks. The h0 is initialized to some constant, and then you have to do this repeated computation. So step 1 is you have some initial state, and then you have these helper functions, and the state is being initialized using this helper function. So the code is again here. I have this quickly browse it so you can look at it later. So you have some initial state which is the 16 32-bit blocks, that is the input message, input block. Then you are going to run a loop for 64 times where you had that those helper functions, they being evaluated here. This is a small sigma 0, a small sigma 1. You see these XORs happening here. And then you add many of those UL32s. Why are you adding those many UL32s is you have this addition. This addition is a sum of UL32s. So you do this internal state initialization of this, where you had this XOR which I showed here. You can check that in the slides. So similarly, you can go through all this. So maybe I'll just skip that because it's not very instructive. So I've given the code links for each of the parts of the SHA-56 circuit. So because I think I promised a walkthrough of the SHA-56 circuit here. So you can look at that. It's not doesn't make for good instruction in a live lecture. I will skip that. And similarly, some other helper functions as given the relevant code. You can check that out. I fix this, something went wrong. So let's look at, okay, how can I prove these circuits? Suppose you wrote a circuit, how can I prove this wallpaper circuits? So the main thing you have to do is you have to implement, you have a structure and you have to implement something called the synthesize. You have to implement a circuit proof. And once you implement that, then you can prove using either Groq16 or Spartan proof systems. In that repository which I shared, there is one example of Groq16 and one is Spartan. Let's look at a simple circuit. It is just going to prove that y equals x cube plus x plus 1, where y is a public input. So you are proving that you know some x which can be such that the public input y is the cubic x cube plus x plus 1. So the way the synthesize is, this is a structure and it seems to have some phantom data. So what is happening is that the structure, there is no state in this structure. So, but it has to depend on the circuit has to depend on a field. It is with respect to a particular field. Now, because there is no dependence of the field in the structure, you use this phantom data, which is a Rust primitive. It says that suppose you have a structure and you want that structure to depend on a type. but your structure contents don't have anything which depends on the type. You can create something called a phantom data type, and you can put that generic type in there. So this cubic circuit now depends on this phantom data prime field through this this phantom data. It depends on this prime field using this phantom data. And then synthesize is it's a single function. I allocate a variable which has a value of 2, f of 1 plus 1, and then I take 2 square and 2 cube. I calculate by using these helper functions which are there allocated now. Then I allocate y as x cube plus x plus 1, and finally I enforce a linear constraint, R1CS constraint, that the value of the variable y times the value of x cube plus x plus 1 times 1 is equal to y. This is a single R1CS constraint. Then finally here I want the y to be a public input. So it is right now it's an auxiliary variable because it was allocated using alloc. So there is a helper function called inputize which will make it a public input, and then you can check this. You can run this circuit. Let's run this circuit in using something called Spartan. So this is that cubic circuit here. Circuit, the same synthesis which I showed in the slide, but here I have the proving part of it. So I'm using something called Spartan 2, which is a repository which is maintained by Microsoft. So here I'm initializing the circuit as a cubic circuit, and I'm initializing it to a default value. Then I have to produce something called the prover keys, that is prover and verified keys are generated as part of the setup. Then I generate the proof. This RES will have the proof, and I use snap proof to prove that, and then I unwrap that to get the proof. And then I can verify the proof using the verifier key. But the main thing is that the IO, the second argument to verify, has a scalar 11, because my circuit was using 2 as the input for x. You notice here f of 1 plus 1. f1 is the one element in the field, so I'm using 2 as the input for x. So 2 cube plus 2 plus 1 is 11. So this verification step it's providing it has to provide a list of field elements. It's providing 11 as y was the only public IO of this snark. So I'm putting the value 11 here, and it will pass. I can so cargo run and it finishes running. If I change this value to, say I change this to 12, they run this, then it says it failed. So assertion failed. So the proof verification failed at line 58, which is this line. So this way you can check once you have, so the main thing was that where is bellpepper being used? We are using bellpepper to write the synthesize function. And once you write the synthesize function, you can use multiple backends. In that repository, I've shared a .16 backend also. So the .16 backend was so that's a more complicated circuit. It's a double SHA-256 hash. This thing opens. this. So here I have the SHA-256 double SHA-256 gadget, but I'll create a circuit called my circuit. In this case, the my circuit has some pre-image, and the circuit which is used by this is I'm going to use Grok 16 to prove this. It doesn't need that prime field and the phantom data thing. But again, the synthesize is I'm implementing circuit for my circuit, which is doing the synthesize, and it is checking that. You can check it later. You can checking that the public input is in fact the hash of some pre-image, and you can run this also. So it is generating the proof, it is verifying the proofs and so on. So you can run this also as target. And it takes some more time to run because Grok 16 is much more computationally intensive than Spartan. And I think that's all I had. So the one thing before I end is that there is this repository called bellpepper gadgets, and there are many already circuits which are written like SHA-1, SHA-512, TECHAC, then non-native arithmetic and 82551 and curve operations, Merkle proofs, and more contributions are welcome. I should note that SHA-1 is a gadget which I contributed, and SHA-512 was an MTech student of mine, Varun. He contributed that. And non-native arithmetic and 82519, we were building this for our own some research, and we contributed because Lurk Lab they offered to review our circuits and give us feedback on the Rust and also on the cryptography. So if you go to this repository, you can see that Varun Thakur is an MTech student in E department. He has some latest commit there, and you'll see I have some contributions, he has some contributions, and all the crates are available here. So there is many other like SHA-1, SHA-512 and so on. So when you have these building blocks, you can say some interesting things about some real world statements. So that is why we are building this, and there is another library called Circomlib which we want to achieve parity with, and hopefully we can add more to this. So if you are interested, please reach out and I can suggest some circuits which you can write. So the resources are, these slides are here. Again, just go to my homepage and append bellpepper. Then this code which I showed you is here. Bellpepper and Nova, the folding scheme, which expands the range of applications you can prove, a range of statements you can prove using R1CS is here. And also there is a fork of Nova called RCBO, which is, so I mentioned Supernova, which is non-uniform IDC. So RCBO has a implementation of Supernova. It's maintained by Lurk Lab. So they consider themselves a more adventurous fork of Nova. So they try out many ideas and then they backport those ideas to Nova. But Nova doesn't have a Supernova implementation, but RCBO has one. So if you're interested, you can go there. Yeah, so that's all I had. So.